Okay, so I hope our 2 week 2 weeks off or whatever was okay. Everything good with stuff from last week? Box plots and standard deviation. We're all good. Okay. So why do we find a standard deviation? What's the purpose of finding a standard deviation? Come on.
See if it matches the empirical whatever.
That's an application, the application. But what's the general principle behind finding the standard deviation?
How far everything is away from the mean.
Okay, it's a measure of spread. We're kind of taking the typical distance points are from the mean. So the mean kind of tells us where the center of our data lies, and the standard deviation tells us maybe a typical distance that points are from the mean. So of course some points will be close to the mean and their distance from the mean will be small. Other points are far away from the mean, so their distance from the mean is large. The standard deviation gives us a, quote, typical distance from the mean. And we do that whole process of taking the distance from the mean, squaring it, getting kind of an average, and then taking the square root of that. Okay, is that good? Standard deviation? Okay, then what do we mean by describing a distribution? Well, what is a distribution?
Different curves.
Okay, so we've got maybe some curves and stuff, but the idea is you've got this numeric variable, and we look at where the data lie. Maybe the data, most of the values of the data are large, and they're all very close together. Okay, so maybe if I have a really easy test and most everybody gets 100%, then the distribution of test scores, or the distribution of data, would show a lot of people getting 100%, maybe 90%, and something like that. So we would have a narrow distribution. On the other hand, if I make kind of this general knowledge test with lots of questions, we might have the scores might be all over the place. Maybe the average score is like a 60%, and some people getting up to 80%, and some people getting as low as 30% or something, and there's all sorts of different scores. The distribution of scores then would be wide with a lower center. Therefore, so a distribution just tells us how the numbers in our data look. Okay, so those are kind of the big picture concepts that I don't want us to forget when we've talked about chapters 1 and 2, okay, or especially chapter 2. Okay? Because sometimes it's like, oh, this is how you find the mean, and this is how you find the median, and the standard deviation, and we get caught up in these formulas and values and things, but we lose sight of the big picture. So, okay. Standard deviation is a measure of the spread. All right, today we're going to move into probability, okay? And a lot of times statistics, well, almost every statistics class has us learn probability, and we feel like, oh, it's like the same subject, but they're actually two very different disciplines, okay? Well, as much as different subcategories of math can be different. But probability is a separate topic from statistics, but statistics uses a lot of the ideas behind probability to do its, to make the conclusions about the data. Okay, and so last week, or from chapter 2, we learned about describing data. Learned, distributions, and we have measures of center, dispersion or spread. Okay, and then we also talked about the shape and stuff. So anyway, this is describing data. This is for numeric at least. And then today we are going to learn probability. Okay, and probability tells us how likely is a certain event to occur. Okay. How likely is an event? Alright. And so at this point, it might seem like these two things are disconnected. Yes, we have a question.
Sorry, I had a question about chapter 2 actually.
Okay.
If the standard deviation is like the measure from the mean, why is it that we divide by n
Minus 1?
minus 1 instead of
Okay.
just n?
That's a very good question. Okay. The reason why we divide, okay, so this is, so again, the standard deviation is kind of like, it's the square root, I can spell square root, square root of the average square distance from the mean, right? So this is going to, so side topic, back to chapter 2, but this is good, okay? So it's the square root of the average square distance from the mean. This is the concept behind standard deviation. If you look at the process, that's what you're doing. You're taking the distance from the mean, you're squaring it, and then you add them up, and then you're basically taking the average, except if you took the average, you would add up all of those squares and divide by n, okay? The reason why we're dividing by n minus 1 is because we don't actually know the true mean, okay? Because the standard deviation tells us what the average distance, or this square root of the average square distance from the mean of the population. That's what it's really going after, okay? We want to know what's the typical distance from the mean of the population. But what we're using instead is we're using the mean from a sample, okay? So the mean from our sample should be close to the mean of the population, but it might not necessarily be exactly the same. Does that make sense? Okay, so maybe the average height, if somehow we were able to measure all, 150 million women in the United States, measure their height, maybe the true average height, I don't know, I'm making up a number, is 5'4.5". Okay, 5'4.5", let's say it's that, 64.5 inches. But then let's say I took a random sample of 20 women, and I measure their height, and the average height of my sample is 5'4". Okay, when I calculate the standard deviation, I'm using 5'4" to decide how far everybody is from the mean. Okay, so the distance from the mean for my sample is actually not really the true distance from the mean for the population. Okay, and so there's some complicated math involved that goes into calculus and things like that. But it turns out to compensate for the fact that we're using the sample mean rather than the population mean, we should divide by n minus 1. Okay, so divide by n minus 1 because we use the sample mean rather than the population mean. When we say, what is the typical distance from the mean, okay? Okay, does that make sense? Yes?
So does that mean if we did have a population?
If we did have the population mean, you would just take your actual data points and you take the distance from the data points from the actual population mean, and then you divide by n, okay? But you wouldn't be using your sample mean. The sample mean wouldn't be part of your calculation, okay? This is, if you're curious and if you like math and calculus and all of that stuff, you can go onto Wikipedia and look up something called Bessel's correction. This is the, that's what it is, all right? It's not for the faint of heart, so, you know, don't bother. Unless you're into that kind of thing. If you are, you know, all the more power to you. If you're a stats major, you're gonna have to take a class where you learn all of this stuff, and that was my least favorite stats class. So. But anyway, okay. So going back to what I was talking about, okay, is it alright if I erase this so I can use the board to talk about? Okay, so going back, I don't know, maybe you have to rewrite part, just write chapter 2 and chapter 3. Okay, so chapter 2 we learned about describing the data, and chapter 3 we're learning how likely is an event to occur, okay? What's the probability that some event occurs, okay? And we'll talk about that concept in a little bit here. So these are different things, but we tie those together, okay? When we use inference, okay, which will come later in like chapter 6, 7? I don't remember. Okay, inference. Basically, we're going to ask the question: how likely is it to observe our data? This is the probability part. How likely is it to observe our data? Okay, so the how likely, this is the probability. And then the observe our data, this is our describing data part. Okay, and this is the driving force behind inference. We're going to be asking how likely, you know, is it to observe our data? Someone says they flipped a coin 100 times and it landed heads 70 times, which we would say, oh, that's more than it should, right? If you flip a coin 100 times, you're expecting it to land heads about 50 times. Okay, well, if you don't know that, we'll learn about that in probability, okay? But if somebody says they observed 70 heads, we'd say, oh, that's unusual. With inference, we can say, how likely is it to observe 70 heads? Well, that's part of the data, but inference, okay? And so actually, chapters 3 and chapter 4 is a specific set rule within probability and things like that, and the normal distribution and whatnot. We'll get into that. But this is why we learn probability, which is today we're going to learn all these rules, and then next week we're going to learn a specific probability thing called the normal distribution, which shows up all the time. Okay, so let's talk about probability. Okay, so we already kind of talked about, when we talk about probability, we're asking how likely, what is the chance something occurs, okay? How likely is an event? Or what is the chance? What is the chance, or what is the probability? That blank happens. Okay, these are the types of questions we ask with probability. Okay. So we say, we define an event. Okay. Alright, so if you pick up a different textbook, they're going to have different notation. Okay. So our textbook uses E for event. A lot of other textbooks will say A, event A, okay? And A could be anything. anything you want it to be. Define some event, okay? And then we say the probability of that event probability of A, sometimes it will be written without the R, and they're the same thing. Okay? So don't say A and probability of A are the same thing. Okay? A is the event, and then this is the probability that the event occurs. Okay? There's a distinction. So A could be the coin lands heads. Then the probability of A, if it's a fair coin, is 0.5. Okay? It doesn't make sense to say A equals 0.5. A is the coin lands heads. And the probability of A is 0.5. Okay? That's an important distinction. Sometimes students, their notation gets sloppy. Or it could be, you pick any other letter, okay? B could be the probability, not the probability, okay. B is the event that I reach into the bowl of M&Ms and I pull out a blue M&M, okay? Draw a blue M&M. Okay. So then the probability of B is whatever, I don't know, 0.15. I'm making this up. This is a made up number. If you're like, how did you get 0.15? I made this up. Okay. I don't know. We can go to the M&M factory and ask. What percentage of your M&Ms are blue? 17. Okay. How many M&M colors are there? 5? Blue, red, orange, yellow, green, brown. 6. Yeah, you can get custom M&Ms now. You say, I'm getting married and I want everybody to have M&Ms with my initials on them and wedding date, and I'll do it. All right. Okay. So okay, what does it mean? So let's go back to this. So we say probability of A is equal to 2.5. This is, and we're going to say A is the coin lands heads. What does it mean for the probability A equal to 0.5?
50% of the time.
Okay, half the time, or 0.5 of the time, it lands heads. And what do you mean by the time?
50% of the number of flips.
Okay, so if I flip it once, how many heads am I going to see?
Possibly.
0.5 possibly.
No.
So if I flip it once, I'm either going to see 0 heads or 1 head. And if I flip it twice, how many heads am I going to see?
Probably 1, but possibly 0, 1, or 2.
0, 1, or 2. Okay? So, of those, only one of the outcomes is half the time it landed heads, right? So when we say, so I mean, colloquially, or casually, we might say this is, we will see the coin land heads. And you said half, but I'm going to just write 0.5 of the time. Okay. Which is totally fine, But when we say 0.5 of the time, we don't actually mean for one coin flip or for two coin flips or for even after 100 coin flips, we won't necessarily see exactly 50 heads and 50 tails. Okay? This is I might have mentioned this our first week. We're going to take this very classical approach to statistics and probability, and we're going to take something called the frequentist view. Okay? And so from the frequentist view, of probability says, what we mean by of the time is if I flip the coin an infinite number of times, okay? This is, if I could flip the coin an infinite number of times, okay, it would land heads 0.5 of the time. That's the frequentist view, coming from the idea that we could do this frequently, a whole bunch of times. Okay, but of course nobody can flip a coin an infinite number of times. Well, Chuck Norris facts might disagree, but so we can't do anything an infinite number of times, and half of infinity is still infinity, and that doesn't really make sense. But it's the idea that if I did this a whole bunch of times, it would be 0.5. So so the reality is this. Okay, I flip the coin once, and maybe I will see 0 heads. Okay, and that would mean the proportion of heads of times it landed heads observed, okay, is equal to 0, right? And let's say I flip the coin 5 times, and let's say it landed heads twice. 2 heads observed. Okay, so I'm going to just write the observed proportion of heads is equal to 2 out of 5.40. Okay, and maybe after 100 flips, maybe I observe 53 heads. Okay, my observed proportion would then equal 0.53. Okay, and the idea is, as I do more and more and more coin flips, this proportion that I observe will approach whatever theoretic proportion, okay? As I do more and more coin flips, the observed proportion of heads approaches the theoretic That good? All right, and this concept, this is known as the law of large numbers. And a lot of times we will call the observed proportion the empirical probability. Okay? And so another way of stating the law of large numbers is that as we increase the number of trials of a random experiment, the empirical probability approaches the theoretic probability. Okay, so outline law of large numbers again. Number of trials increase. And again, you know, so the frequentist view of probability, as we're learning, is that, you know, when I say probability that it lands heads is 0.5, that's under the assumption that if I could do this an infinite number of times, the number of heads that I would observe would be half of infinity. Okay, I mean that sounds silly, but that's what we're saying here. Okay, now of course, that doesn't always work. When we say, you know, like if you go to the doctor, if someone goes to the doctor and they're saying you're, I don't know, you've got this disease, and they're saying your chance of surviving past 6 months is 40%. Okay, what does that mean? Okay. Well, the frequentist view, when we say the probability of survival past six months is 40%, the frequentist notion would be, let's say we could pause time right here and create an infinite number of parallel universes. Okay? And so this is a little science fiction, but in 40% of these parallel universes, this person would live past 6 months. And then in the other 60% of parallel universes, this person would not. Okay. Now, of course, we don't have parallel universe, or if we do, we're not aware of it. And you know, we're just in one world in one universe, and so whether this person actually lives past 6 months or not is either going to happen or not going to happen. But that's the idea of the 40% here. Okay. That's the frequentist view. Okay. The other viewpoint is the Bayesian view, and that's kind of an idea of belief. I stake about 40% belief in the idea that this person's going to live past 6 months, but that's an entirely different, I don't know, different approach to the subject. Okay. All right. Is this okay? All right. So so maybe some of our first exposure to probability is probability of simple events. Okay. And simple may not necessarily be simple in that, but the idea behind simple here is that every outcome is equally likely, okay? So this might be flipping a coin can be considered a simple event. You have two outcomes, heads and tails. Okay, rolling a die. 6 outcomes, all are equally likely. You can get 1, 2, 3, 4, 5, or 6. Okay? Drawing a card. Yeah, basically all of those games of chance at Las Vegas, most of them are simple events, right? Roulette wheel. You've got 1 through 36, the 0, and the double 0. Okay, 38 outcomes, all are equally likely. Okay, so for a simple event, when we say, what's the probability of some event A happening, this is equal to the number of outcomes in A divided by total number of possible outcomes. Alright, so if I say, what's the probability of a coin landing heads? Well, there's one possible outcome that's heads, and there's out of a total of 2 possible outcomes, so that's how we get 0.5. Is that good? What's the probability that on the roulette wheel, the roulette wheel lands red? Alright, so how many spaces on the roulette wheel are red? Does anyone know? Nobody goes to Vegas? Nobody plays these games? Alright, there's 18. There's 18 red spots, 18 black spots, and 2 green spots, okay? So the probability that the wheel lands red, 18 out of
38.
38, great. And I don't know, that's 47 or something like that percent. I'm going to Las Vegas this weekend, tomorrow. I'm meeting up with my friend from college. He's my best man. I don't know if we'll play roulette. It's just throwing money into the fire, basically. But it's fun. Throwing money away? Yeah, no, just kidding. Alright, so the roulette wheel lands red. The probability that the roulette wheel lands red is 18 out of 38.47. Okay, so these are simple events, okay? What is the probability? Okay, let's say we're draw a card from a standard 52 card deck. Standard 52 deck. Okay, what's the probability of drawing a red face card.
26/52.
So a red face card. So
face
face
card.
card is Jack, Queen, or King. Now Ace, I don't consider face card because there's no face on that card. But
6 out of 52.
12 over 50.
a red face card.
6 out of 52.
6 out of 52, right? It's Jack of Hearts,
Oh, that's
Queen of
right.
Hearts,
Yeah.
King of Hearts, and then Jack of Diamonds, Queen of Diamonds, King of Diamonds. Those are the only red face cards in the entire deck. There's 6 of them. There's 52 cards total. 6 out of 52. Here. So you can look in the book, they give you more examples. These are traditional probability examples. Because our book says probability for the life sciences, they give you all these biology examples, which are fine, but I think maybe a little more obscure. Okay. Okay, let's just let's talk about probability trees. Alright, a probability tree is a tool that we can use to calculate more complicated probabilities. Okay. It's just a tool. Help us find more complicated. Okay. So now we might not have simple events anymore. Okay. So simple events, all the outcomes are equally likely. That's not so much the case when in real life. Okay. So let's say, okay, let's say I've got a standard 52 card deck. Now let's say I'm going to draw 2 cards. I draw out 1 card, and then I keep that and I draw another card. And let's say I'm only looking at the color of the card, whether it's red or black. Okay? And we look at the color of each card. Okay? So what are the possible outcomes?
Black or red?
Black or red, but at the end of drawing 2 cards, what can I possibly end up in my hand?
0, 1.
I could have 2 red cards,
0.
1 red and 1 black card, or 2 black
cards.
cards, yeah? And well, what's the probability of each of these things happening? Okay, so I've got three outcomes. Okay, I've got 2 red, 1 black, and 2 black. This is how it can happen. Okay, so, and what's the probability of each of these things happening? Okay, well, these are not all equally likely, or are they? Well, they're not. Okay, so this is how we can use a probability tree, okay? We're gonna draw, this represents the first card that I draw, okay? When I draw the card and I look at it, what could this card be? What are my possible outcomes here?
Black or red.
Yeah, the card could be red or the card could be black, okay? What's the probability that it's red?
1 out of 2.
Yeah, okay, so I'm gonna write 26 out of 52. That's equal to 0.5. So I write the probability of getting this event along the branch that leads to, this is the possible outcome. So the possible outcome is red or black, and I write the probability of going down that branch on there, okay? And then likely, same thing here, I got 0.5, okay? 26 out of 52. Okay, and so this represents all possible outcomes, so these two things have to add up to 1. Okay, let's say I drew a red card. What's the probability that the next card I draw, well, the second card can either be red or black, yeah? What's the probability that the next card is red? 25 out of 51. It's no longer 0.5 because after I've taken the red card out, there's 51 cards left. 25 are red, 26 are black. So here I've got 25 out of 51, and it's going to give me some number. And I've got 26 out of 51. Another number. They're both close to 0.5, but they're not exactly 0.5. So 0.49 and 0.51. Okay, that's with a little bit of rounding. Okay, and then if the first card is black, the next card could be red or black. And what's the probability of drawing the red card? 26 out of 51, so this is 0.51. And the probability of drawing a black card, again, is 25 out of 51, 0.49, okay? And again, notice that at each node, the probabilities of all the branches coming off of that node add up to 1, okay? And if we were talking about like the individual values of the cards, I could draw anything between an ace and a king, and so I would have 13 branches coming off. I didn't choose that because that would be too much work to put on the board. But I would have 13 different branches coming out of a single node, and all the probabilities of all of those branches would also add up to 1. Okay? But here I've just picked where it's just 2 possible outcomes. Okay, so what's the probability of getting red, red? Well, I just go and I multiply down the branches, and I do 0.5 times 0.49, and I get 0.245. Okay? The probability of going first drawing red and then drawing black is 0.5 times 0.51, and that's going to be 0.255. Probability of drawing black and then red is 0.5 times 0.51, which is 0.255. And then the probability of drawing black and then black is 0.5 times 0.49, 0.245. Okay, and all I've done is I've gone 0.5 times 0.49 for red, red. For red, black, 0.5 times 0.51. For black, red, 0.5 times 0.51, and for black, black, 0.5 times 0.49. To get all of these things. Is everyone good? Any questions thus far? Okay. So, what's the probability of getting 2 red? 0.245. What's the probability of getting 2 black? 2.4. So I'm breaking my own rule here, right? I've got to put probability. 2 red doesn't equal 0.245. Probability of 2 red is 2. And probability of 2 black is 0.245. And what's the probability of drawing 1 red and 1 black?
0.25, 1.
Right, this one plus this one, okay? If we're not caring about which one was first and which one was second, I would add 0.255 plus 0.255 and I'd get 0.51. Okay, so this is what we can use for a probability tree. Okay, it's a tool that helps us answer questions for slightly more complicated situations. Yes?
So all that also has to add up to 1, correct?
Yeah, all of that also has to add up to 1, okay? Well, because these are, it has to add up to 1 because these are all possible outcomes, okay? If I didn't list a certain outcome here, like if I left off this outcome, then it wouldn't add up to 1. But if I list off every single possible thing that could happen when you draw 2 cards, that's what has to happen. Okay, let's try a more complicated probability tree. Okay, so let's say, what's a really common disease or virus? Chickenpox. What percentage of the population have chickenpox? Do we know? Any idea? All right, let's say 30% of the population has had chickenpox. Okay, so this might not make sense, but we're just gonna go with it, okay? Let's say there's a test where we draw blood and then we put it into the thing and it says, oh, you have the chickenpox virus in you or you don't have the chickenpox virus in you, okay? But let's say this test is not very good, okay? So today if you took a test like that, it's pretty accurate, okay? But let's say this test makes mistakes quite a bit of the time, alright? So we take a test to determine if someone has the chickenpox virus. Okay, and so let's say if the person has actually has the virus, the test will report positive uh, 98% of the time. And if the person does not have the virus, this time when it reports positive, it's a mistake, right? Still reports positive, a mistake. 15% of the time. Okay. Does this make sense? So it's not a very good test, but it's good for our example. All right, so what percentage of people will get positive test results? Okay, see if you can answer this with a probability trait. Alright, some of you guys are still working. That's okay. Maybe you're struggling, you're getting stuck. That's okay. Or maybe some of you got the answer, 0.399. Excellent. Let's see. Okay, so we are going to say either someone has the chickenpox virus or they don't in real life, okay? So if we actually knew the truth, we've got has chickenpox virus, okay? And this would be does not have the virus, okay? So what's the probability that we select someone and this person has the chickenpox virus?
0.3.
0.3. Yeah? Okay, so what number goes down here?
0.7.
0.7, because these two things have to add up to 1. Okay, question? Any question there so far? Alright, so then what do I put at the notes here? If somebody has the chickenpox virus, what could happen with the test results?
Positive.
Positive or
Negative.
negative? Positive or negative. Same thing here. Okay, if they actually have the chickenpox virus, what's the probability that it shows positive?
0.98.
0.98. And this would be
0.02.
0.02. And if they don't have the chickenpox virus, what's the probability that it's positive?
0.15.
0.15. So these are all directly from my problem description. And this thing down here would be
0.85.
0.85. Questions or confusion on anything this here? Alright, so there's two ways for someone to end up getting a positive test result. They actually have the virus and it shows positive, or they don't have the virus, but because this test isn't very good, it still shows positive. So let's see. We go so the probability that someone has the virus and shows positive. So this is probability that someone has virus and shows positive is equal to 0.3 times 0.98. Alright,
0.294.
0.294. Great. Okay, is that okay? Alright, so then what's this? This is probability that someone has no virus, has no chickenpox virus, and still shows positive, and shows positive. So this is 0.7 times 0.15. So this is 0.105. And then I add these two things together. Alright, so the probability that someone shows positive is equal to probability that someone has the virus and shows positive, and probability that someone has no virus and shows positive. So this is equal to 0.294 plus 0.105, and that's how I get 0.399. Okay, so then just very quickly, what's the probability that someone gets a negative test result?
0.601.
0.601. We could go through the process and do 0.3 times 0.02 plus 0.7 times 0.85 and add those up. Or I could also say, well, if you didn't get a positive test result, you got a negative test result, and everything has to add up to 1, right? So then I could just do 1 minus 0.399, or what added to 0.399 gives me 1, is going to be 0.601. So the probability of a negative test result is equal to 0.601. How are we feeling? Okay. All right, let me complicate this a little bit further. Okay, so let me just I'm going to just put the probabilities right here at the end of the lines. What is this one? 0.595. Okay, so that's what would happen if I multiplied down the line. I did that. Okay, I'm going to ask if someone gets a positive test result, what is the probability that they actually carry the chickenpox virus? this question even make sense? Does anyone have an idea?
0.294 divided by 0.294 plus 105.
Yeah, so it's 0.294 over 0.399. So the answer is this. 737. But let's talk about this, okay? So this is saying, okay, you get the test results back. The test result says positive. Okay? The test result says you have the chickenpox virus. So the test result says positive. But does that actually mean you carry the virus?
No.
No, this test is a junky test, right? It makes mistakes for those who don't have the virus 15% of the time. Okay, so you could be someone who actually has the chickenpox virus and the test says positive, or you could be someone who doesn't have the chickenpox virus, but because this test is a junky test, it comes back and it makes a mistake and says positive. Okay, so there's two ways for you to get this positive test result. We want to know what's the probability that you're in the group that actually has the virus. Okay, so this is equal to the probability. So the answer to this question is the probability that someone has the chickenpox virus and tests positive divided by the probability of just testing positive. Okay? So on the top I'm putting 0.294. Why am I putting 0.29? I'm sorry?
I know somebody
Okay.
says I said positive.
Why am I putting 0.294 and not 0.3?
There's only
Because 0.3% of the population has the chickenpox virus, but why am I not putting that on the top?
Because it's only 98%.
Because this group, the 0.006, these people get the false information that they don't have the virus, okay? So here it says if someone gets a positive test result, what's the probability that they actually have the chickenpox virus? These people don't get a positive test result, so they're not part of my question. They're not part of my question. Okay? So 0.294 of the entire population has chickenpox and gets a test positive, divided by everybody who tests positive, which we established in the previous group is 0.399. So this is 0.294 divided by 0.294 plus 0.105, which is 0.294 over 0.399. And that gives me 0.737. Alright. And one more. If someone has the chickenpox virus, what is the probability this person gets a positive test result? Okay, so this looks similar to this, but I've just kind of switched things around. So it says, if someone has the chickenpox virus, what's the probability that this person gets a positive test result?
Didn't you put that in the question though?
It's written right in the question. And it says, if the person actually has the virus, the test will report positive 98% of the time. So the answer here is taken directly from the test question, and the answer is 0.98. Okay? But be sure you can tell the difference between this question and this question, because they look similar, but they're also distinctly different. Okay, and then just also to further differentiate the other question that also looks similar but is very different is what is the probability that someone has the chickenpox virus and tests positive. Okay. And the answer to that is 0.294. And that's from our probability tree after we've multiplied all of these things out.
I don't understand the difference between someone has the virus, it's probably to get a positive result, and then what's the,
Oh, you got it?
Yeah.
Okay, because it's a good question. It's because these three questions, they look similar, but they're asking different things, and it's important that we can tell the difference between the difference here. Okay. Maybe is this okay? All right, so maybe I'll write up a problem here, and then I'll ask a whole bunch of questions, and you try to get the answers. Does that sound good? Okay. Okay, so this, I'm completely making up numbers here. I don't know if these numbers are actually any good or not. Okay, so let's say we're dealing with a pregnancy test. Okay, so pregnancy tests today are pretty good. Okay, if you're not pregnant, they almost never tell you that you're pregnant, except in it happened in 30 Rock. But, she was eating some kind of fast food or potato chips. That was anyway. All right. Okay. So this is an odd situation. Okay. So we will say a woman believes there is maybe believes is not the right word to use, but it is. But okay, a woman believes there is I don't know, 20% she is pregnant. Percent chance that she is pregnant. Or probability. Okay, so some women, they take precautions, and so their probability that the probability that they believe they're pregnant is close to 0 or 1 or 2% or something, and other women are trying to get pregnant, so they're hoping this number's higher. But for whatever reason, some woman believes there's a 20% chance that she is pregnant. Okay, so she decides to take a test. Okay, she takes a pregnancy test. Okay, and let's say that if she is pregnant, it will report positive. It will report, positive or whatever, 2 lines. 99% of the time, with probability 0.99. Okay, and and if she is not pregnant, it will mistakenly report positive we'll say 1/2 of 1% probability 0.005. Okay. So we will say if the test comes back negative, what is the probability she's actually pregnant? Okay, so that's the question you have to answer.